Let me show you how to be a good Bayesian.
Hey folks, what if I told you that one of the most interesting barriers to Bayesian adoption in the real world is not mathematical, it is the file format. Today's guest, Andreas Munk, has a PhD from UBC, where he worked under Frank Wood and published at NeurIPS on probabilistic programming and amortized inference. And then he co-founded Evara, a startup bringing Bayesian inference to enterprise inside Excel. Yes, Excel. We get into inference compilation in this episode, what it actually is, how it relates to amortized inference, which you may have heard about already on this show, and how PyProb, a Python package to do exactly just that, open source, makes all of these practical. We talk about probabilistic surrogate networks, and then we make the leap to the harder question. How do you take all of that beautiful research and explain it to a CFO who just wants a number? That last part, communicating uncertainty in enterprise settings, is honestly where I think this episode really shines. I hope you enjoy it as much as I did recording it. This is Learning Bayesian Statistics, episode 155, recorded March 19, 2026.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. What's a Bayesian? It's someone who cares about evidence.
Welcome to Learning Bayesian Statistics, a podcast about Bayesian inference, the methods, the projects, and the people who make it possible. I'm your host, Alex Andora. You can follow me on Twitter at Alex_Andora, like the country. For any info about the show, learnbayesstats.com is la place to be. Show notes, becoming a corporate sponsor, unlocking Bayesian merch, supporting the show on Patreon, everything is in there. That's learnbayesstats.com. If you're interested in one-on-one mentorship, online courses, or statistical consulting, feel free to reach out and book a call at topmate.io/Alex_Andora. See you around, folks, and best Bayesian wishes to you all. Hello, my dear Bayesians. Just a small update about my agent skill project, because a few weeks ago I published my first agent skill, which was the Bayesian workflow skill, and which scored 100% on every eval I designed. And then the brilliant Maximilian Goebel actually used the skill on a real model, and it broke. You may remember from Max's appearance on the show that we're working together on something that's called the soccer factor model. This time, in this iteration, we're working on a hierarchical ordered logistic model predicting match outcomes across 5 European football leagues, and Max ran the same prompt through 2 agents, one with the skill, one without, and a third agent compared them blind. The good thing is that the skill nailed the fundamentals like prior predictive checks, non-centered parameterization, strict R-House threshold, and a properly identified model structure. But interestingly, the unskilled agent did a few things better, especially reaching for the regularized horseshoe prior for high-dimensional features, while the skill I designed did not even mention sparsity priors. And that made me laugh quite a bit, because that meant that one afternoon of real-world testing by Max revealed more gaps than 3 rounds of synthetic benchmarking I had done. So what I did is shipping V1.1 of the skill within the week. Now we have new critical rules, sparsity priors, classification evaluation matrix, identifiability checks, lots of new stuff, also coming from some advice from Osvaldo Martin, friend of the show. So the big lesson here is evals are necessary, but not sufficient. Most importantly, get your tools into real hands early. If you want the full analysis, you'll get the blog post in the show notes of this episode, because now we have a blog section on the learnbayesstats.com website, so feel free to check it out. And on that note, let's continue with today's show. Andreas Munk, welcome to Learning Bayesian Statistics.
Thank you very much, Alex. It's a pleasure to be here.
Yeah, same. Thank you for taking the time. It's going to be a an interesting episode talking everything uncertainty, and you certainly have experience with uncertainty. So this is great. Let's start as usual with your origin story. You know, can you tell us how you transitioned into the world of statistics and eventually found yourself at the intersection of probabilistic programming and deep learning, which is something you're really passionate about?
I most certainly am. Yes, it's a funny story actually. Well, I don't know if other people find it funny, but I certainly do looking back at it. So I've always liked mathematics, physics growing up, and going through high school, it's been the things that I enjoyed the most, the kind of logic, puzzles and problem solving. I'm sure a lot of us sort of start off like that when you get into Bayesian inference ultimately. But after I did a 6-month trip around the world right after high school, which is pretty normal in Denmark, where I'm from, I got this weird idea that I was going to do business. And I actually even applied for that for college. And I failed to recognize a certain requirement, which was there's a certain level of sort of English you need to have and all the sort of other subjects that are just prerequisite requirements. And I didn't have it at the right level. And I didn't see that. I applied for the one thing, and so I didn't get in. So I had to find some of the free spots, which obviously it was a pure sort of spur of like almost hybris at the time. But I ended up going into engineering because that was one of the few places that had any spots left. And it was Earth and Space, Physics, and Engineering. That was the program. So we're still not quite at Bayesian yet. But my plan was to do that for a year and then switch back and upgrade the English level. But I ended up, not surprisingly maybe, to just really enjoy that program, and so I stayed and stuck with it for the entirety of my bachelor's. So it was sort of a weird segue into getting back into physics and engineering. And so Denmark doesn't have the biggest space program, so we cooperate and collaborate with, of course, the ESA program and NASA as well, I think, for some programs. But mostly what we did was looking at satellite images of Greenland and sort of other analysis in that way. And so doing that, I got into more programming because that was part of a lot of the analysis that we had to do. And I wanted to get more into that for a master's. And instead of starting over from computer science, I switched over to the sort of machine learning mathematical modeling program that we also had. And sort of that was my weird segue into it. It was also, I could do more programming without starting all over again. And it was in that program that we had this course, Bayesian analysis. And I had no idea what this was at the time, but it was much more theoretical than the sort of hardcore deep learning. You sort of build some neural networks and you sort of train it. I wanted to do sort of more core statistics, which was crazy. I don't know why I thought I wanted to do that at the time, but that's what I wanted to do. And it was taught by Ole Winter and Archie Vitari. I believe you've been chatting with him as well. He was visiting for 6 months. So he taught that whole course, and we went through the book, the Bayesian analysis, data analysis book, which of course, probably a lot of us know. It's a brilliant book. And we did all the STAN programming, and that's how I got introduced to probabilistic programming. And I just fell in love with it. I thought it was incredible that you could sort of embed uncertainties and statistics into the languages themselves and then just run them and you do inference. It was the decoupling of what it's like to do the modeling and have inference sort of be separate, I thought was incredibly powerful and incredibly fun to play around with. And so I decided I wanted to do research within this area. And that's basically how it all began. And so after my master's, I applied to various different schools, and I got in touch with Frank Wood, who was at Oxford at the time, who was moving to UBC in Vancouver, Canada, and setting up a totally new lab. And so I ended up joining him that was back in 2018, I think. That's a few years ago now, to do probabilistic programming. And they just, I think the year before, written a paper on inference compilation, which is amortized inference, where you combine probabilistic programming and inference with neural networks. And sort of that's how it all started.
Wow. Okay, so you were one of the first students from Akivetari, if I understood correctly. Damn, this is pretty cool. Pretty cool.
I thought
Dude.
I really, really enjoyed that course. It was the
Yeah,
beginning,
I
so
guess.
it was
Mm-hmm.
yeah, and they did a wonderful job teaching. It was so
Yeah.
much fun.
Mm-hmm. Yeah, and I can definitely see also like the influence of entrepreneurial studies in your background, and we'll get that later. But you've actually founded at least one company, so like this is not surprising to me. Um, and also what you're trying to do with Evara is actually related to something you noted already in much of your work, which is a lack of real world Bayesian applications despite its universal applicability. And of course, it's something I resonate a lot with because this whole show is about making Bayesian statistics more applicable, more widespread, and just showing people it's not that hard. And it's actually easier than the stats you're used to. It's just these stats you're used to seem easier just because they are more familiar, but not because they are intrinsically easier. So in your experience, what are the biggest adoption barriers for people outside of academia?
Yeah, it's a good question, and I wanted to touch, based on what you mentioned, which is indeed going through this my studies and trying to find applications of Bayesian inference. I think that's really sort of maybe a good starting point, which is of course something you do in academia all the time. You develop all your methods, your theories, etc. You got to showcases and sort of benchmark it, etc. And I remember how peculiarly difficult it was, and sort of still is, to come up with the sort of example use cases. And I think it's, for me at least, it seems harder to do in the Bayesian context than, let's say, the more of the frequencies context because of the model components. I think that's precisely part of the point, and it's going to tie back into this adoption barrier, I think, in a bit. And indeed, after I graduated, going into the entrepreneurial space was similar to, I think, a lot of us, is that it's surprising that it's not more proliferated out there. It's incredibly powerful, and I think there are many instances where Bayesian inference is a brilliant tool and a framework to use to solve lots of different problems. And I think we do it all the time subconsciously as just humans. I mean, it ties back into the belief updates of what we expect, and you get like observations, and you have to update your priors, which are your beliefs. And most of us probably don't think about it, but most people don't formalize it, obviously, and you don't write these things down, and there's no label for it really. But I think it ties into that particular problem, which is it is a different approach to the sort of statistical thinking. And so if you are a statistician, you're sort of already primed to think in this way, and you question sort of everything, and you're uncertain about everything. It's almost like your world now. You doubt everything in your life, which is sort of almost ironic. But you're also driven to, I think, look at the problems from different angles. But if you look out into most everyday life, you don't think about the sort of differences between the frequentist maybe way of thinking about a particular problem and then the Bayesian approach. I mean, there's no label for it, and you don't formalize it. And there's also no tools for it. That's the other thing, right? And we all know statistics is hard. It's like the one thing everyone talks about in terms of, I mean, ask anyone who doesn't do statistics regularly. Even people that do statistics, it's just the math can be crazy, right? So, I mean, people are like scared of it almost, which is quite, I think, understandable. But when you bring Bayesian into it, it's like no one thinks about it, and now they have to change how we think about these different problems in a way that is almost counterintuitive, even though, like you said, it's intrinsically not necessarily harder, but it's a different way of thinking about the world and your problems, which I think most people just don't do. And it's very hard. Even I've tried this to talk to people who are, scientists maybe in different fields who do statistics. And it can seem like the difference between Bayesian and frequentist methods is almost, it's subtle. Well, it isn't, obviously, but I think it can seem subtle because this prior that we have to define and think about with the model, it's still something we need to come up with ourselves. And so how is that really much different from maybe as like a statistical test? And for someone who knows about it, it seems obvious. Of course it is, but it's not clear that I think it can seem like a detail almost, because it's not clear how much of a massive difference it does in terms of the underlying theory and how you sort of deal with it, and how it's not a statistical test. In fact, it's quite the opposite. It's about specifying those prior beliefs rather than testing out a hypothesis. But there's overlaps, and that's where I think it can get really difficult to sort of really find and grasp the nuances. Unless, like you do, and probably many of the listeners, you think about these things all the time for years, and you get bogged down on those details. So I think that's part of that adoption barrier. It's just not, I think statistics generally, in many cases where you should use it, it's not used already. And everyone talks to frequentist, I think, a lot of the times. So how do you then introduce this Bayesian method, which I think it's just difficult to sort of wrap your head around.
Okay. Yeah. I can get what you're getting at here for sure. I think the education work that you and I are doing in the whole community I'm interviewing here is extremely important precisely for that reason. And actually a major theme in your work is bridging the gap between deep learning and probabilistic programming. And I think it's extremely important because here we're talking more about technical people than beginners, of course. Like if you're familiar with deep learning methods, by definition, you're a fairly technical person. But I think it's also important to address these two audiences. So the more beginners that you mentioned, that show is also about, and also the more technical audience, which is also part of my audience. And first, I try to do that too in my own work, bridging that gap between deep learning and probabilistic programming, because I think there is a huge potential here for great models. But I'm curious, in your case, why do you see this synergy as so important? And what does deep learning provide that traditional probabilistic programming engines lack?
So I think it's a good question also. And I guess one of the core themes that, always comes back also as almost like a counter argument to Bayesian inference is the computational, requirements and how fast does your inference engines and algorithms converge in the back end. And I think you've talked about this multiple times already as well on your podcast, Alex. And I think there's many cases where you can speed up the inference task. Potentially, that's important thing to bear in mind, right? With using and leveraging neural networks. And I think one of the difficult things to consider is whether you're doing a one-off, let's say, inference problem where you have one observation, or like set of observations, and you have to do this in one go, but you don't want to necessarily redo the inference task for different sorts of observations. Then it's harder to imagine maybe in those cases where neural networks can come into play in the way that certainly origin that I've been working with in. But if, let's say, you wanted to do the sort of in the same model, do inference with many different kinds of observations, then you can think about these amortized inference methods where there's probably going to be certain, underlying patterns in those posteriors. You could at least envision that, where you can maybe train a neural network to, for instance, be the proposal distribution for those proposal distribution-based algorithms. And so you can imagine if you can build your model, you can, for instance, you can produce samples over a wide range of your priors. And now you can produce in your model all of your observations, right, from the likelihoods that you've also defined. And so you can use those sort of methods to train the neural networks to infer the posterior distribution across all of these different observations. And so now the underlying assumption is that you have a really good proposal distribution, for instance, for important samplings. Not to say that you should just use important sampling, but that's a straightforward way that you can use these proposal distributions. So I think that's a very, very interesting avenue, and that's some of the things that I've been working on exactly. And I think one of the more interesting things that I started thinking about before I graduated is maybe similar to all these like LLMs, maybe you can amortize not just for a single, inference problem, but maybe you can do it across different tasks as well if you make these things big enough. And you might be able to start sharing them across, different industries and different inference problems, etc. So that it's not sort of, you aren't limited to just using them whenever you do multiple inferences, but you can actually use them for different types of inference tasks. I think that would be really interesting.
Yeah, and I like how you've set us up here is actually very reminiscent of amortized Bayesian inference that we've talked about already on the show. That's something you work a lot on, and so I'll put these episode 107 and 151 in particular with Marvin Schmidt and Jonas Arruda, who are both working on the base flow side. So if you guys, if you folks, if you all listeners want to have references about amortized Bayesian inference, episode 107 with Marvin, and if you want to actually see live how to use diffusion models in Python with a live demo, episode 151 with Jonas is going to be extremely helpful to you. Here, we are going to talk about that with you two, Andreas, because you work a lot on that. You've had a lot of work on that, especially I think your most cited paper is on what you call inference compilation, which looks a lot like amortized Bayesian inference. So let's explain that. Like in simple terms, what is inference compilation? Is there any difference with amortized Bayesian inference? And how do we use neural networks, which are a deep learning method, to amortize the cost of inference so that it becomes faster over time for our probabilistic models?
So I should just clarify, I didn't write the paper on the inference compilation. It was sort of subsequent work. I think the year before it was some of Frank's other students, Tuan and others that actually wrote that paper. I think the paper you're referring to is that's just two, but it was part of this Loomis project, which is the inference problem there is the particle decays inferences given the sort of signals exactly. And there was a big simulator, but that was sort of a follow-up or extension of the work that was inference compilation. And so just briefly for context, because I think, one of the probabilistic programming languages that I've been working in is PyProb. It's a language that sort of was created out of the inference compilation theory to sort of really be targeted to do inference compilation. So that is precisely the reason you think. I think we mentioned that it's similar to the amortized inference is because that's exactly what it is. You train neural networks to do amortized inference, and the neat thing about probabilistic programming, as you probably also talked about, is that you get these graphical models. And so you can sort of define the entire space of which you would have to sort of construct these neural networks, regardless of the inference problem that you're looking at. And you can sort of construct these similarly to how you can deploy the inference algorithms. You now also have this automated way of constructing and training these amortized inference neural networks that you can use, for example, with the importance sampling as a backend engine, or others for that matter, of course, wherever it makes sense. So that's exactly what that work is all about. One of the interesting aspects there, though, when you think about probabilistic programming, is that I don't know if you probably have talked about this also, but when you consider the difference between the low and high order probabilistic programming programs and languages and what they support, some of them are unbounded, right? So you don't know, you can't just compile the whole program sort of at a sort of compile time into the static graphical model. You have to do it dynamically. Turing-complete programs, Turing-complete languages, you can't even guarantee that they will halt. And so part of the inference compilation aspect is how do you do this dynamically as you're just generating, right? You have to come up with the mechanism where these neural networks can grow dynamically as you also generate samples over time. because you don't need to just generate 1 million. What if you want tomorrow to generate 10 million? Like, you don't want to start over necessarily. So that's a core part of that work, is how do you construct and train neural networks on the fly while making sure that you can maintain the conditional dependencies between all of your random variables without losing those dependencies, right? You can't constrain the neural network to sort of lose the dependencies because they can be arbitrary, right? The 1 millionth variable could depend on the, number 1 that's generated, and that's part of that. That's part of that work. And sort of I think the first paper I wrote was about using attention mechanisms rather than the LSTM-based mechanisms that was used in the original work, because of the potential long-term dependencies, and maybe you're forgetting the sort of, especially if you have 1 to the million, are you actually able to remember that well throughout the LSTM? So that was some of that first work that I did.
Yeah, which is really fascinating. And so is this from this project that you started working on PyProb, which is an open source package that I put in the show notes, and I think that's how these work came to be. And I think this is a very interesting package. So I'd like just to talk about that a bit right now, because I already have a lot of questions about these papers, and why you made some choices and not others. But I think it's going to be more concrete if we talk through it with PyProb, because it's actual code that people can use in their own workflow. So for those who are not familiar with PyProb, what is the big picture goal of it?
Yeah, so the big picture is to do amortized inference with inference compilation. That is the main and the core purpose of it. It's designed around how to construct these neural networks. That is actually the long and short of that. So it's if someone wants to sort of explore how you can train the neural network in a way that it's sort of embedded into the probabilistic programming language itself, PyProb is a great place to start with that. Now, it's obviously maintained by the lab, and I wasn't the original author. That was Gunesh Baidin, who was the main, first author also of the paper you mentioned that I've been working on afterwards. We called the Lumis paper, but that's actually another paper. But it's those 2 papers. There's 2 papers that came out of that same project. One is about how to scale these like PyProb up into sort of multi-core, multi-CPU, multi-GPU distributed compute, etc., which was a whole big effort on its own as well. But that, I think, is still maintained by the Play Lab out of UBC. So yeah, I think if you have the link there, you can easily go there, and you're always welcome to reach out to me as well. It's I am intimately familiar with the language. I'm not so involved with it anymore, mind you, I should say, but it's very much still there.
Yeah, and so yeah, what can you give us the elevator pitch for it? When would it be useful? When do you recommend using it? When not to use it? And what are its current limits, so that listeners can get a lay of the land?
Yeah, if you want to do amortized Bayesian inference in programs, especially where, even if you can map out the entire graphical model, it's a great language for that, to play around with how to train neural networks. And especially if you want to play around with how can you come up with different architectures or different designs for constructing these neural networks. As it's open source, it's a great place to get started. I think that's again, that it is the core mode. There's also the PPX plugin, I think, where you can, I didn't play around with that too much, but I believe you can even plug it into, I won't say all, but many other languages as well. So there is a bridge essentially between. So it is written in Python. So that's the other, I guess, neat thing. If you like Python, it's already in Python. So that's nice. And uses PyTorch as well. So I'm sure a lot of listeners out there probably use PyTorch. So if that's what you find interesting and want to play around with, I think it's a great language, and I quite enjoyed playing around with it. And I don't know if they've been pulled it in yet, but there's also automated surrogate modeling, which is the another use of neural networks. So it's not amortized inference, but if you have programs where certain bits of computation in the, let's say the simulator is very computationally expensive, you might want to train a surrogate neural network to speed up that computation if you're okay with the trade-off of the approximations, of course, with the outputs. And so that was a follow-up work that I did afterwards, where similarly to doing automated inference, you can also do automated surrogate modeling for the entire program.
Yeah. Mm-hmm.
That's also part of the, I don't remember which of it was in the fork or something, but it should be there somewhere.
Yeah. Yeah. And I'm actually curious, in your experience, which kind of models do you recommend using with amortized inference? Which kind of situations and models are most appropriate for these kind of methods in your experience?
Yeah, I think that ties back to what we talked about earlier, which is the repeated inference tasks. Right. So one of the examples that I worked on myself is curing of composite materials. So one of the things that you usually do when you are trying to figure out how to construct the plane, part of that is to ensure that you can simulate what it's like to create the materials that it makes the wing, for instance. You want to make sure that it's produced and it's created properly. And so you can simulate, the thermodynamic mechanisms as you basically, if you put it in a big oven, that's what you do with these composite materials. And one of the things you might want to make sure of is that the internal temperature reaches the right, how should I say that? It can't be too hot or it can't be too cold. There's a pretty sort of narrow window of the internal temperature so that it's constructed properly. Now, you could, of course, drill into it, while it's inside the oven, but then you might break the materials. So the idea is, can you infer the internal temperatures by just observing the surface temperature, for example? And you can use a simulator for that. So if you simulate the process properly, you still end up with a latent inference problem because you don't observe directly the actual temperatures internally, but you can infer them. And so that was the first one of those first sort of examples that I used. And here it's an obvious sort of maybe use case where every time you need to do another measurement with, say, as a different plane wing or something like that, well, that's a new inference problem. But the simulator you're doing inference in is the same. So it's the same model. So here is a perfect example of where you can train these neural networks and you can reuse them over and over and over again and speed up the inference task by orders of magnitude.
Well, yeah. Yeah, okay, so that definitely pairs with what Marvin and Jonas told us, which is basically if you have ideally big data and fixed model in a way, so something like a physics model or something like a model that doesn't change a lot, but you do have data that changes a lot because you have a lot of it, then amortized Bayesian inference is going to be one of your best bet.
Actually, I should actually emphasize, you don't need real data even. This is what's so amazing about simulators. You generate it.
Right.
But you just run the simulator, because if the simulator is good, which, in this case, it's a highly sort of high fidelity physics simulator. It's using the right differential equations, etc. So you can just keep running the simulator and it generates all of the possible outputs that you might want to condition on. And so you can construct your own data set, which is the amazing part.
Yeah. That's always really amazing. I think for most people using the Bayesian framework, this won't be something really different from what they are used to, prior predictive samples, posterior predictive samples, they're always in the framework already, even if you don't use amortized inference. But if you come from a frequencies framework, this will definitely be something that's going to be quite weird and very empowering, I think, because it's much more intuitive when you think about your models that way. And I think it's also very useful to, select features, for instance, when you're working on a model, because then one of the bars that each feature has to pass is, well, does that feature has actually a clear generative story in your model? Does it explains something about the outcome that other features don't yet.
Mm-hmm.
And that's a good bar to try and pass, because if it doesn't, then why is it in your model? Probably it's creating problems more than solving things. So it's a good, more intuitive way of thinking about feature selection than just thinking about it from a statistical perspective. It's like, well, if it's passing that threshold, then it's in there. Okay.
Mm-hmm.
Why?
Yes.
Yeah, and that's
No,
harder
exactly.
to explain to a business stakeholder.
Oh,
Definitely.
definitely. Which is why I always like Bayesian inference for that reason. It sort of forces you to think about those sort of things, right? You're building the model,
Mm-hmm.
so you have to be quite, like, it is almost baked into the process that you need to think about these sort of things.
Mm-hmm. Yeah, no, exactly. And so maybe to close up on PyProb, how can interested listeners get started with PyProb?
Go to the website. That's basically the best starting point. And like I said, you can always reach out. You can reach out to the current maintainers. I don't know. It's a while ago. I looked at it last time, so I guess you have to just double check what the contacts are. But that would be the best way to do it, is to go there and look at some of the examples. There are examples inside the repository as well for how to build models. That's the easiest. It's the real problem is, of course, and that's, I guess you asked about the constraint earlier. It is the PlayLab that maintains it, so it's not as a big repository with as such a big community as well. So when you use it, it's similar. You have to just appreciate that it's not like there's a million people that keep sort of updating it all the time, and etc. So that's the that's the only caveat. But otherwise, that's the way to do it.
Yeah. And I can confirm that there is quite enough resources on PyProb on the website to get started with it. So I think it's a good starting point. And now, listeners, you know more or less the use case where it's going to be helpful. So if it's one of yours right now, definitely check that out. And actually, you mentioned that already, Andreas, but you've also worked on probabilistic surrogate networks for simulators with something that's called unbounded randomness. I didn't know about that. So yeah, can you explain that? What are these? How do these surrogates manage to stay fast while retaining the interpretable structure of the original simulator?
Yeah, that's a good question. It's also the main difficulty of the work. So it was inspired, by the way, of that same Turing problem, because that simulator is quite expensive to run, and so it was actually, and it was also from even the Interlumis project as well. It's the same problem. You've got some big simulations with some big computational blocks in there, and you just don't always know exactly where they are. And if you've got millions of lines of code, how do you sort of extract out the exact pieces that you want to surrogate over? It can be a huge endeavor. And so the first pass is, of course, can we just build a surrogate model for the entire program? Right? That certainly covers those cases. And the problem there you immediately run into, hence why unbounded randomness, is because, well, if you're in a probabilistic programming setting and it's Turing complete, well, you don't know when the program halts, or if it halts, or how many latent variables are being produced. And you don't know the order of the latent variables. And essentially, if you think about it, it's like you have to infer the branching structure as well. If you've got if statements, while loops, etc., when do you exit the loops, etc., and so on and so forth. And that was the real sort of underlying sort of theoretical part of the work, both technically but also a little bit from the theoretical side. So that work primarily was a matter of how do you construct these sort of neural networks that can, similar to the inference network, grow. But the difference here is that, and I don't know how much you've talked about this before on the podcast, but one of the ways that you reason about the sort of stochastic structure of your programs is we need to be able to identify all your random variables, for one. And so you use these addresses, which are these unique identifiers, that you construct. If it's dynamic, you construct them dynamically, for instance, is a way you can do it. If it's a bounded program, you can again compile it, and so it becomes a little bit easier. You can sort of have a little bit more control, I suppose, depending on how you decide to do it. But in this case, when you do it dynamically, again, you can't guarantee either that it's the same order every time. And in the inference compilation case, it's much easier because, well, you infer given the variables that you produce during your trace, and the program itself still runs concurrently with the inference program. So again, if you think, let's say, let's just use importance sampling as the example, right? So because you need to calculate, the joint probability at the top to calculate the weight, the weight for the inference algorithm, and divide by the proposal distributions PDF that you place on the samples that you proposed. Well, to calculate the joint distribution of the program, you actually need to run the program. So you can imagine if you start the program execution from the beginning, whenever you hit a random statement, like a sample statement, instead of sampling from the prior, let's just call it prior because it's obviously not always in the prior sense because they're all conditionals, right? But whenever you hit such a point, you will then, instead of sampling from those conditional priors, let's call them, you instead query the proposal distribution, right? So the neural networks that you've trained. But then you then continue executing in the original program. And so every step of the way, you can compute the joint probability and divide by the proposal probability as well, and construct this dynamically. You can maybe you can imagine this. It's hard to sort of visualize maybe, but that's the way you would do it. The surrogate problem is different because you're replacing the program. So you can't use the program to sort of guide the structure and produce the variables that would sort of follow from a given sample. So that is the main problem that we have to figure out how to solve. And well, it's not maybe too surprising. The sort of way to maybe do it, a way to do it is to do a classifier. So you can imagine given an address and everything that came before it, because you need to consider that, let's say, a branching structure, an if-else statement, could be some arbitrary computation of all of the previous sampled values, whether explicitly or implicitly. And so the neural network needs to try to predict which of these branches, let's say the if-else statements, that you need to then enter in quotation marks, of course. Now, there is no if-else statement in the way that certainly we did it, but you're mimicking it by then predicting those addresses that might come from either of those two branches. Of course, the immediate criticism would be, well, the program is deterministic in terms of choosing the branch. But the philosophy, I suppose, that you would have to accept is because you don't observe everything and you don't know you haven't mapped out all of the cases in your program and know from the sort of enumeration all the values, which you can't do because if you sample from a Gaussian, it's continuous, so you can't figure out exactly the cutoff point by just testing it. So maybe a stochastic approach to predicting these branches is not unreasonable, and that's how we did it. Now the real problem is also you don't know necessarily how many how many branches you might enter. You can imagine a while loop where the value determines when you exit. Right, so you could sample initially, let's say, from a Poisson distribution, and then given the value, that determines the number of iterations of the while loop when you break it out again. And so you need to come up with a way where, let's say, a previous random sample could produce an unbounded set of transitions to other random variables. And we don't know about this number beforehand, so it really was a matter of how do you sort of expand the space of classifier values that you don't know beforehand. And so one of the things we did is we thought about, well, although it's not, maybe measure theoretically equivalent, because it isn't, but you can imagine that you have a classifier that predicts the transition to known transition up to any given point in time during training. And then you always have a holdout probability mass on other yet unseen transitions, but it's like the collection of all of those that you may or may not have seen yet. And every time you see a new let's say, transition, that would be like a new class, like a new type of image, for example, if you think images, you would break off almost like a stick breaking process, some of that holdout probability mass, and begin training on those transitions as you see them. And it's sort of probability measure preserving at the time of splitting, but it's not quite the same as if you had known the transition existed beforehand and trained from the beginning. So it's not entirely unbiased in that sense, but it otherwise is quite, I think, quite neat. And it works, I think, quite well, actually.
Yeah, this is super interesting. I don't think we covered that, at least that deeply yet on the show. So thanks a lot for these details. I think it's, this, of course, is not something that you're going to apply all the time, but it can really serve you when you're in the cases where it's actually most needed. So actually, would you mind enumerating and summarizing these cases where you think these kind of methods are going to be most helpful for people?
Yes. The answer is I'm not entirely sure. At this point, it became a theoretical science. We needed it for a simulator, and so we developed it. And of course, it's a probabilistic programming, so we have to be general and agnostic in how we construct these methods. We had the use case originally, but to be honest, it's not. I think there's many cases where you would need to do it, especially again if you need to surrogate over programs where you don't know the execution paths. But maybe you want to actually split out, instead of thinking about it probabilistically and simulating all of the, let's say, random samples, if you wanted to speed up a computation where you just care about the branching structure, that might be a more interesting application. But to be honest, it's not something I've been thinking too much about since it was, I liked the theoretical aspect more at the time of figuring out how to do it in the first place, so it's a very good question. And if anyone thinks of something, I would love to hear it as well. I think that would be lots of fun.
Yeah, for sure. So please, folks, do that. Do reach out if you end up working on that for sure. And Andreas, any reference that you can add to the show notes about that will be super interesting. I of course put the link about the proceedings of machine learning research that you worked on in the show notes. But if you think there is anything that I missed and that would be helpful for people who want to dig deeper on that topic, please feel free to add that to the show notes.
Of course.
And something you've actually also written about is the mental shift that's required to move from single number predictors to belief updating frameworks, like the Bayesian framework. So in your experience, why is accuracy often the wrong metric for a Bayesian practitioner?
Yes. I guess that actually also goes back to sort of maybe the adoption barrier. So I guess if you think maybe enterprise, and now this relates a bit to sort of maybe my experience from sort of the entrepreneurial space that came after the studies of trying to, I guess many of us has the same goal. We want to democratize Bayesian inference. I think it's underutilized. It should be used basically everywhere when it obviously makes sense. But if you think about what enterprise does today, I'm sure you can attest to that also. They all want to hear about accuracy. And it's a rational thing to think about. Is you have a predictor. If you want to predict the future of your enterprise, let's say financially speaking, you're predicting the sales or your budgets or your P&L, or if you're considering your loans or your interest rate, all that kind of good stuff. You want to have a thing that's perfect. That's fair enough. But on the other hand, it's also a weird thing because we don't observe everything, in which case there's uncertainties just almost inherently. And so I think in many cases, what we really want, in fact, is obviously this distribution of what we think could actually happen, which is also really, I think, the only proper way to even consider risk, right? Unless you know your uncertainties about your predictions, how are you going to assess whether or not there's a risk involved? Because if your model is perfect, there's effectively zero risk, right? That's almost obvious. So if there is uncertainty, well, that's what you would want. So what does accuracy then really mean? Because now it's about, if you have a distribution, that's what you would want. Well, then the accuracy is a question about how accurate is your distribution, given some true distribution, which usually we don't know. but people don't think about that sort of accuracy. They want to know how good is my sales single number predictor, which fits well into, the frequentist methods. And it's also maybe why they can sometimes be more appealing. It's also an easier, I think, often narrative, even if you want to, let's say, sell a product in this regard, right? It's we've got a predictor, and you can also measure some R-squared value or some accuracy, which funnily enough can also be gamed in themselves, which is funny because of how do you measure that it's accurate? It's like, well, R-squared, absolute values, whatever, but no one talks about that. It's just better than the others, which is also a funny thing. But if you talk about like creating something or inferring a distribution, I mean, no one knows what accuracy means in that case. I mean, for most people. That's why I think it's a very interesting and a funny, somewhat like a paradox in some way, that we think about these accuracies, but we're not talking about the accuracies that I think oftentimes are more important, to be honest. And I think Bayesian inference is great for that, but it's you have this barrier, which is like, if you don't think about distributions, but we think about accuracies for a single number, now you have this. If you try to convince or persuade or proliferate these ideas, it's like, well, I want a number, and now you don't even give me a number. And then I'm unhappy. Like, why would I even care about this now? Because it's like, now I need to understand why distributions are important, and and it's not. I think it's a tall order in many cases, which I think is also understandable. There's a lot of thinking that you would have to do and shift that mindset, which is not about whether you could do it. I think everyone can. But there's an effort in trying to change the way you think about your problems in everyday life.
Yeah, no, for sure. And I think that's where also your background, where you're preaching academia and industry is extremely interesting to talk about here, because how do you recommend doing that then in an enterprise setting? How do you explain the value of modeling uncertainty to stakeholders who are used to goal targetings and point estimates rather than simulation and probability distributions?
It's a good question. I think that's honestly the biggest problem that as a community we need to figure out how to solve. I mean, and I'm curious what you think about this too, Alex. Which is, whenever we talk to ourselves in the community, these things are obvious, right? It's we all think about this all the time. It's part of the reason that we love it. I mean, I guess you probably think the same. Once you start thinking Bayesian, you can't stop. It's like you think about everything this way, which is almost also annoying. You doubt everything in some weird way, and you also doubt because we know humans can't do Bayesian inference mentally at all very well. We're really bad at it. And so anything I think about and my predictions, and now I see some piece of evidence, I doubt my own immediate update because like, I don't think I can do this right. But exactly, how do you do that to everyone else out there without sounding like that they're doing things wrong? Because that's the other thing. It's not like you can't say that Bayesian inference is not necessarily right. Again, it's an approach to certain sets of problems. And I think in many cases it's the right tool, and it's the best tool we have to reason about many of these things. But you can't say that frequentist methods, for instance, is wrong. It isn't. It's a different framework, and it's totally fine to use it. But when you're trying to, let's say, either sell a product or convince people or persuade people to use this, if they're using frequentist method, you're also asking them to be like, well, maybe we should try something else, which can sometimes be, well, why would I bother? And if you try to convince them, almost, it's in some cases you might need to try to tell them that maybe it's not the right way that they're currently doing it, but that can be, I think, difficult to acknowledge on the other side as well, and you can come across as a bit of a, I don't know, you know better sort of thing. Which is not, I think, quite the right way to do it. I haven't quite figured it out yet. I think it's one of the hardest things that we face as true Bayesianists, is how do we sort of proliferate these ideas without sounding both arrogant. And it ties back to the use case problem, I think, honestly, which is, it's also very, very hard to exemplify the value, because you're also in a space where you can't, quote unquote, prove it. There's uncertainties no matter what you do. So if you predict, optimize this and you're going to get more sales, but here's your, the error bars. And then it doesn't perform as well as you maybe did last year, but then it's probably going to be, you're going to be faulted for your method, not because it's inherent to the prediction. It's all well within the error bars. What actually happened, it's baked into the system. It's supposed to be that way. So it's also hard to think to prove the value, because there is no accuracy number. If there was an accuracy number, that's part of the way you could sort of initially get people on board much more easily, because you can, if you say you have a low error prediction on your sales, well, that sounds nice. I'll believe you. If I believe you, I might want to use it. So I don't know how to do that, honestly. It's part of the things I did. That's the thing I think the most about all the time these days.
Yeah. Mm-hmm. No, I mean, this is definitely a hard question, and that's why I ask it. I've definitely seen a lot of scenarios throughout my career, because I've done a lot of consulting before working full-time for different companies. So yeah, I've seen a lot of different scenarios and stakeholders. So I can't say that there is one recipe that's going to work all the time, because it depends a lot on the people you have in front of you. Unfortunately, sometimes you have dishonest or insecure stakeholders. This is the hardest cases, because like you have to take into account much more than just the technical aspect of the job. So it also becomes much more of a politics job than a technical job. And it definitely depends on who you're talking to and what the actual situation is. The hardest is when you definitely need to not make the stakeholder look bad. This is the hardest situation to navigate.
Mm-hmm.
But if you're, let's say you're in a, like most of the time you're in a situation that's pretty normal, right? Where you have in front of you someone who wants to learn, who is pretty scientific. Like when you do consulting, most of the time you're in front of technical people and some business people. And when it's the same, like if you're one of the data scientists in a team, you talk to your boss who is fairly technical, and you also often talk to other people who are not product managers, or I don't know, like whatever you have whoever you have in front of you. Most of the time, people are just, well-intentioned. They want to learn and they want to solve a problem. That's just what they want to do. And if they are not technical, even if they are technical, what usually my arc for doing that is, acknowledging the tension, but then offering the resolution. Because it's true that the tension is real. You have some business stakeholders who want certainty. Not all of them. I've had a lot of business stakeholders who actually love when you're talking about uncertainty and you're estimating it. These are the easiest ones, because they are like, oh yeah, I love that Bayesian stuff. I don't know how to do it, but that's great that you do. So please, lay it all over the analysis. But when you have people who really want just one number and certainty, then I think also trying to acknowledge that false certainty is worse than acknowledged uncertainty is something that's important. And then reframe it, don't give them a distribution. Give them a decision tree level summary, like there is an 80% chance that this player outperforms the threshold, like this player or this product or whatever. And practical tools I use a lot of the time is use scenarios instead of intervals, right? So usually I love having an optimistic base and pessimistic case, and what drives each of the scenarios. This is much more useful than giving non-technical people intervals. And then visualizations, of course, on top of these scenarios for each scenario that make the uncertainty feel like information, not like noise and something that's giving you paralysis analysis. And yeah, in a way, I think the deeper point is that uncertainty quantification builds trust over time. Yeah, so that's I think this point is more real when you're embedded in a science team inside a company, much more than when you're doing consulting where things go much faster and on shorter timelines. But when you are part of the science team in a company, then also like when people know that when you say you're 70% confident and you're right 70% of the time, then people start listening to the 40% cases too, let's say. Right.
Mm-hmm.
Of course, you need time for that. Like, it's not, building trust takes time. It can be compacted if the company moves very fast, but still, it's not something you can have from day one. So yeah, like, and most of the time, from what I've seen, is that a lot of the stakeholders will respect honest uncertainty more than false precision, especially after being burned by overconfident models. So in a way, having overconfident models is also something that's serving you as the modeler, because like if people have been burned by that, then they know you cannot go too far either in the direction of certainty.
Yeah, and that makes that. I mean, of course, that makes a lot of sense, and that's exactly. I mean, it resonates a lot with sort of what we've experienced as well. The so the not the caveat is not the right phrase. What I find is the real, for me. So I should maybe start from the sort of the current goals that I have now, and sort of why we're doing Evara now, which is this business that I've started after I graduated. But it all comes from that sort of my passion for obviously Bayesian inference, which we all share, and the goal that I thought was going to be achieved years ago, which is, why is probabilistic programming not used everywhere? It's in the languages. We all use this language anyway, but they're usually not used either, which is perhaps not too surprising, because you need to be a programmer, for one, and two, they're still very statistical. Right, you still need to know about statistics. So you have this weird Venn diagram of like statisticians that also know and cares about Bayesian inference, and then pretty good programmers, and then that sort of intersection there is not a particularly big one, I think, across the world, certainly. So it's not, I think, too surprising on one side, and yet I think it's so important to have this as almost like a probabilistic like calculator, if you want to call it that we should all have this. It's almost like, if I'm using my estimating it sort of really anything, I would like to know my uncertainties about that. Like if I'm looking at my monthly budget, why not have my error bars for myself throughout the entire accumulation of all of my uncertainties, which is about how much heat do I use, how much electricity do I spend, how much gas, how much do I drive, and all that kind of stuff. And there's uncertainties in all of these different components, and they all add up to this monthly, expenses, including, potentially income uncertainties about my, job, and so on and so forth. And that seems to be something that I would just, if I do a budget like that, I would just want that inherently. Like we all do it now. We write it in some sort of program somewhere on our machine computers, and we get some number out. But that's not, we all know that that's not going to be the real number. It's just some sort of weird gauge. But probabilistic programming promises that essentially that you can just, even if you don't do inference, just Monte Carlo simulation, the sort of base no observations, you just create and see what is my expected sort of plus or minus expenses every month. And then you do inference once you start to actually observing your total, expenses every month, right? That's the other thing. You don't even need to really do much updates once you build the model, unless there's something fundamental into your behavior that changes the way that you might want to update certain mechanisms. You can just put in your expenses every month, and then it will adjust those uncertainties for you. And it's a perfect almost example also, because one of the big problems, as we've talked about, is the computational scale and how fast you converge. But it's like, if the baseline is no uncertainty, I would rather have something that might have converged somewhat, but still give me some level of estimations of my my budget. And it still seems better to me. So it's like the bar almost is very low, because you're not competing against some other very technical solutions here. It's nothing or something. So, and you can just run it longer, And if you do this once a month even, who cares if I need to run it for 20 minutes? I mean, obviously most people wouldn't, but it's just hopefully the example kind of makes sense of like, why not have it? And so that's what I'm really want to do. And it's the problem there is that if you are thinking about, let's say, selling to an organization, now you have to hand over that process entirely. So if you do, let's say, right, the consultancy bit can solve a lot of those maybe friction points, because at least they can offload it in some sense, right? They can sort of get on board with the ideas, and as long as you produce the sort of the results and the outcome, and they just need to sort of take that in, it's it seems logically also sort of more easy, and you won't be as opposed to it. But if you ask them to do it, it's not that they don't maybe like the ideas of it, but it's more like you ask them to do work, which might itself be sort of part of the, not only do you need to try to understand, but you need to understand it enough that you sort of trust what's happening. It's a new tool that you have to use. And yet that's what I find the most interesting. That's really what I want to solve. That's everything I think about these days, is how do we get people to use it and find it interesting and enjoy it and see the value of it without just offloading the sort of that intellectual bit to another entity.
Yeah, no, that makes total sense. And actually, thanks for the segue. That's perfect, because I think it's a good time now to start looking at your insurance pricing demo that you have with Evara, which is the company you founded. But before we jump into the Excel sheet that you have for us, can you set the stage? What are the latent variables we're gonna look at? We're trying to account for when setting, in your example, a car insurance premium.
Yes, exactly. So take it into like this more enterprise-like stage rather than maybe a personal monthly budget. You can imagine if I were to offer, let's say you, Alex, like an insurance policy, just to make it slightly more personal. One of the things that you own a company and you want to insure all of your cars in the fleet of vehicles, so you're a fairly big business. I want to figure out and ascertain how many claims would you do every year, right? And how much is it going to cost every year? And so a simple example like model would be to indeed have those latent variables, which is how many claims and how many vehicles are you going to make claims on in any given year out of the total amount of vehicles that you have. And on top of that, you might have a change in vehicles. So if you have a deal where I need to get an estimate of, even historically, how is your claim history going to change over time as well? And if your fleet grows, how should I expect that in the future? And should that change how much I charge you today? Because I need to predict the potential insurance premiums into the future. And as an insurance company, the important thing is, of course, that there's always risk involved, because how much money do I need to hold in reserve to make sure that I can pay out your insurance claims? That is really the sort of almost the game. So like in insurance, the uncertainty is like very much an inherent problem, right? Because I don't know how many damages there's going to be. And I need to make sure I have enough money, but I can't have all my money said. I need to reinvest my money as well. So this is very much a problem of what is my risk tolerance? Like, do I want to make sure that there's a 99% chance that I will be able to pay everything out? But that might be a very long tail distributions where I can't make any of the money that I've charged all the customers work for me. So that's really the underlying problem. And the latent variables are the metrics about your business that I can't observe. Like the changes in the number of vehicles, right? I can't observe that. And how many of your, if you give this out to your employees and they drive around, like how risky are they in their behavior of driving and so on? And that's some of those latent variables that you would need to infer. And that's the example that we've been sort of looking at. So it's a simplified version of that, where we will be inferring the expected number of claims that you make per vehicle. And then obviously you have this unknown maybe number of vehicles. So you have these risk parameters and the exposure parameters. So these are just insurance, metrics that have been used that you can infer as latent variables.
Yeah, and something obviously listeners and actually people who are watching on YouTube are gonna notice is that you've built this model in Excel, and that's really what Evara is about, actually. So yeah, like if you're free to give the elevator pitch for Evara, and also tell us why you build it in Excel rather than a complex coding environment, for instance.
Well, it's all in the towards the mission of making this system democratic and democratizing Bayesian inference as possible. Right. So if we can, I'm just going to, if we assume that Bayesian inference is valuable, I'll just start with that. The reason we're in Excel is because everyone is in Excel. Right. There's about 1 billion people roughly estimated that has Excel. That doesn't mean everyone's going to do Bayesian inference, but there's estimates that maybe about 100 million people are, let's call them super users or power users, that does actually analysis and can do like fairly complicated functions, etc. within Excel, and you can do your monthly budgets and you do P&L and all of that kind of good stuff within Excel. And part of that mission to make it as simple as possible is to make the interface to the probabilistic programming language much, much simpler. So we've basically made Excel into a probabilistic programming language. But we've tried, the main goal is to make it so that you don't have to think so much about the statistical bits of it. So it functions much more like you used to. And trying to make the, let's say you select uncertainties and you visualize the uncertainties and you call them, maybe you call it a round rather than Gaussian to sort of fit the language that you also use sort of every day that matches these uncertainty-like concepts. As opposed to make it super statistical and you call it a sample statement and you call it an observed statement. And so taking it out of that more traditional probabilistic like programming sort of paradigm to make it not obvious. I mean, the interesting thing is Excel is a Turing-complete programming language. But no one thinks about Excel like a programming language. I mean, who does that? No one thinks about it that way. But you can write anything in it. You've got lambda functions and everything. It would be crazy to write all of that stuff, but some people, I guess, do, but it's not pleasant. But Excel does a lot of good things. Like I've actually come to appreciate it since really working in it for monthly budgeting. I would rather use it for that because it has that visual aspect. But I think it's a great medium, these spreadsheet type programs, to make it more accessible and sort of easy to use without having to be a super detailed technical person in programming languages. So that's the reason why we're in Excel, is to sort of leverage that and embed it into existing like workflows. That's the main reason.
Yeah. That's the answer I had guessed from hearing from you from the past hour. So I'm not surprised, and that's honestly, really great that you're doing that. So actually now let's dive into the demo. You want to share your screen and then walking us through the demo live?
Yes, let's do that. I want to make sure I get the right one here. So this one.
Awesome.
All right.
Yeah,
see if that
perfect.
Pops up correctly. Perfect. Wonderful.
Yes. Yeah, it's in there. Cool. So folks, if you're listening, I encourage you to switch to the YouTube video. And if you're already on YouTube, well, I hope you enjoy looking at Andreas and myself in very close framing for more than 1 hour. And your reward is actually to watch these tutorials.
The reward is spreadsheets. How amazing! It's like the one thing like it's what you've been waiting for, is to look at a spreadsheet. Exactly. Yeah. Good luck if you're listening. Good luck on visualizing spreadsheets. Or at least that's going to be quite the challenge. So
we're all nerds here, Andreas. So we're all happy that the reward is spreadsheet. So don't worry.
Awesome. That's what we were hoping for. So let's just call this Acme Corp, right? So this is what I mentioned. Let's say this is your business, Alex. And like I mentioned, we've got these risk parameters. We've got the annual fleet change. We've got loss per claim. And sort of we might have uncertainties about these sorts of numbers when I need to figure out and predict how many claims and how much is it going to cost me, how much claim in total dollar value are you going to be making every year. That is the sort of predictive task that we're looking at. And we have the years here. Let's just do this as an annual example to sort of illustrate the sort of time varying aspect of this and how you can lay this out in Excel. So you've got let's say the first 5 years onto 24. This is a year old. I should have probably added 25 here, but whatever. And then you might predict sort of into the future, what are the claims going to look like for the next, let's say, handful of years. And we have these different other columns here. You've got the claims and the number of vehicles. So it's because the number of claims you will making is a function of the number of vehicles. So if you have a fleet of so many vehicles, the risk and the rate here that is derived from these two numbers is going to tell us how many claims you will be predicted to make every year. And of course, multiplying the claims by the loss dollar value per claim is going to make the prediction of the total loss for that year. And of course, we can add the total loss up for the entire year and then the prediction for the subsequent years, which will give us the total predicted cost. So this is all just, regular Excel that you just sort of type them into the different cells and you can reference them just like you normally do. It works all that same way. Now, if we then ask, let's say I'm going to charge a certain premium, let's say for the next X years, what is the profit from an insurance perspective going to look like? How much money am I going to make or lose? Right? I can just look at the differences between the total predicted loss to the premium, and that's going to give me the total profit that I'll be making, or a loss, right? If it's the opposite, if your claims are going to be greater than what I'm asking for, that's my risk as an insurance company. I make a certain promise today about what I will be covering for you, and there's going to be some uncertainty about how much you'll actually claim at the end. And one of us is going to make more money from this. That's basically the premise, right, for an insurance company. Now, if we just look at some of these values, let's look at the uncertainty. You'll notice that it's not, and this is hard to zoom that one in more than this, but it's not a traditional just number. We've got this Evara.decline. And this is your priors, right? This is your sample statements that we've created, right? And you'll find these everywhere. You've got an occurrence here as well. So this is a Poisson distribution. So this is like an occurrence. This is how you might think of that. And the fleet change, which is like the growth that goes on every year, is another occurrence. It's another certainty that we have. And you notice, look at the number of claims here. The first one is the starting point. So let's say the first year when we talked, we had 50 vehicles. So there's no uncertainty in that at all. There's no prediction. You just have 50. Now the next year is just a function of our assumptions in the growth. And you can see it references those numbers as you would expect them to. And you have another around here. So now it's sort of the likelihood, right? Because I'm also uncertain about my model. That's the way you might think about these likelihoods. So I might predict that it's going to grow by 2 and there's a 10%. So this is a nice thing about Excel. I can just write this a 10% variation in my prediction. And that's going to give me my predicted number of vehicles. And from that, we can calculate the number of claims as a function of the two risk parameters and the exposures. This is a fraction of the total vehicle fleet, like the number of vehicles you have. And we can then calculate, of course, the total loss that comes from that. And you can accumulate those. So that's just this is the model, right? I've just described the model. So that's basically what we do. And this is the neat thing about Excel. Every budget or P&L or anything you have that has uncertainties and assumption, ask anyone that does spreadsheet model analysis today. They have uncertainties in their assumptions. Well, that's a model. That's basically what we're trying to sort of make explicit here. Now, when you have Evara here installed as we have, we can just launch it. So I'll launch it here first. And that's going to set up the backend and everything internally so that we can actually start to do inference. This is just for the backend that pops up there. So you can see that it actually starts up stuff there that we can communicate with. So it can do inference and everything. Now, you can see we've got a bunch of options up here, but let's just sort of show that you can actually just like sample and show individual scenarios in the entire spreadsheet. So right now, what we're watching here is sort of like the mean or the median number across all of our assumptions, our distributions. If we make them more dynamic and we click next in previous, you can see that all the numbers sort of just change across the entire thing. So this is just one sample for the entire model that shows up here everywhere. And so you can sort of see a result we can plot also, and it automatically obviously relates to each other. It's just Excel numbers. So you can see that these are, we have a real set of numbers. So this is going to be our real data. It's going to be the blue. So I might have done a little too pretty here, but we want to see what happens when you have actuals. So you can sort of observe and do inference. So, but the orange line here are just random samples from my predictions about the claims and the number of vehicles and my losses. And what we will have now is that the blue line is going to represent our real data. So some of that will be observing, and some of it will be a future predictions. So let's start off with doing the Monte Carlo simulation equivalent. Let's not do any observations just quite yet. So we can just look at, from the beginning, what is my total predicted loss? So we can run the system. Now we basically just do random sampling, and it will be generating, in this case, you can see up here, we have 1,000 scenarios that we're just generating. So you can change this number, and we get a nice plot that looks like this. I'll zoom in here so we can actually see them. So you get this sort of histogram of our scenarios and how they're binned in the total loss that I would expect from my model, just a priori from the beginning. And we can slide through the different scenarios that we've generated, which would of course also reflect back into the original sheet. So you can sort of tie the scenarios to where it is on your plots like this. And so if this is my predicted loss, I would use this, for example, to decide what my policy should be. Because this is really where it sort of fits into your talk with Daniel, which is the sort of, what about the decision-making aspect of this? Well, once I have my predictive losses, the question is, where do I put my sort of line of, how should I say that, what am I comfortable with? Like, given these are my losses, how much should I charge you so that I'm comfortable with having a certain probability that I'm not losing more money than more than 5% chance, etc. And so that's the game that I would have to do as an insurance company. If you did the same model, you would have to do the same for yourself to sort of negotiate with me. And we'd have to come up with some sort of like some sort of min-max position where we're both comfortable. Okay, so that's fine. But let's say we want to revisit after a few years. And now you've made claims after the first, let's say the first 5 years. And now from my side, I want to update my model. That's obviously the problem. So now we have inference. So let's say we have our actuals here. So these are the actuals. And let's hypothetically afterwards compare to our predictions for the future. So let's imagine now I've generated a full scenario for the entire years according to the model. So that's a bit of a mock-up set of data. But I can only infer given the observations of the first 5. So we can obviously, what we'll do is we'll add them as actuals. That's just what we call them. It's just observed statements. And we'll note them. And you can mark them like this. There's many ways you can add them as actuals, but this is just one way to do this interactively. And we can record them. And what we see here is now these numbers have changed. And if you look at it up here, you've got the Evara actual, and it references those numbers on that other sheet. And we should do that the same way here for our number of vehicles. There we go. So now we've also observed the number of vehicles. You can do this for all of your actuals. You can do for some, for all, whichever. It's just a model with observations. And so now you have this, at this point, it's like this pseudo state where you have actuals. So it's not inference yet. You still need to run the inference, but it has this sort of pseudo conditional predictions. So, but now we can rerun it, of course, and do just the inference. This is probably programming. Now run it. Now we do inference. And you get the updated posterior, estimated posterior, of course. Right. So before you had this sort of long-tailed exponential kind of looking distribution. And now after my observation for those first 5 years, you get this much more centered posterior distribution, looking more like a Gaussian, it seems, roughly, right? It's obviously it's an approximator. But it has sort of contracted much more around, 1 point, maybe 2. You can look at here at the top, we've got some summary statistics, the mean standard deviation that follows from our scenarios. You can also look at confidence intervals and other stuff, but I'll sort of leave those details for later. But there's other things you can explore. After those 5 years, my expected loss is $1.2 million. And this is roughly 50-50 even down the middle. So a fair bet, quote unquote, might be to offer a new policy where if it's even, it will be about this $1.26 million. That would be the price for this policy. But I would obviously try to make it so that I get a better deal out of this, because you don't see this plot naturally. But the point is, without such a plot, I can't really make such an offer. Like, I can't deduce what is a reasonable risk reward policy offer that I would give you. Of course, if you want to look at the results, so now we go back to sort of this accuracy, but visually we can sort of imagine an accuracy assessment here. So remember, in our actuals, we had those first 5 years, we condition on those, and we have 5 future years. And so in this plot, what we have is the first 5 up to 24, because we have actuals there, they're fixed in time. So our orange prediction is exact. It's just right on top. So it's the next 5 we need to consider how good we are. And before, if you remember, it was sort of going all over the place because it's just general samples. But now you'll see that it's nicely hooked and tied to that beginning. So if you sample through and look at different scenarios, you can see that it fluctuates sort of nicely around those the blue future predictions in that kind of like, actually, like you can imagine like the arrow bars around that in a posterior sense. And you can visualize 8 individual scenarios here. So if I wanted to, let's say for reporting purposes, choose a scenario lies, let's say, way out here in the bottom, let's say a few losses, and I wanted to report that, we go even further down, let's say here, right? So now we have chosen scenario right here. Well, we can now look at this is what that scenario looks like in this case. And it reflects again this posterior sense where it's like the blue is what might actually have happened in this case, but we predicted or assumed it was this, the orange one at the bottom, but it all fits within that posterior notion. It's that in 2024, we don't know what's going to happen. So we have all these possible scenarios, and we might make a decision based off of, we think it's going to be this lower bottom one. But we have accepted at that point in time the fairly large risk that is going to be greater. Because if we go back to the plot here, it's sort of down here in the lower end. There's a big chance it's going to be greater. But that's where the risk reward, question really comes into play. And it's all about your risk profile as a, individual or business or corporation, etc. So that's what we're doing, is that we make this available.
Oh, yeah. Yeah, this is awesome. Thanks, Andreas, for this demo. And yeah, for everybody listening, this is actual Bayesian sampling in an Excel spreadsheet. So this is like, I know a lot of people have been dreaming of that for a long time. Well, this is actually what you're getting here. So that's amazing. Well done on that, Andreas. And I'm curious, like under the hood, how do you do that? Like, have you had to code all of that in? I don't remember the Excel language.
There's a lot of languages and things going on under the hood. It is that's a lot. That's the best thing I can say. There's anything from VBA to some TypeScript, C#, and you name it. There's a lot of stuff that needs to go into that to make it work nicely. I mean, part of the sort of, I can say that certainly the technical, interesting things to think about is how do you make it also sort of efficient to use proper resources? Because you don't, the reason we have an engine that runs in the backend is because you don't want to be constrained by the Excel computation resources themselves. But you also need to make sure that you're not messing up with how Excel functions otherwise, naturally. So it's a non-trivial task.
Yeah, I can guess that. How do you do for like, do you support already net sampling and things like that? And if yes, how do you do that? Like, do you plug to any like probabilistic languages that already exist, like PyMC and things like that?
We've got some of the traditional, typical algorithms put in place. It's that so far it's not been the main focus actually quite yet. But firstly of all, there's a lot of the sort of more straightforward ones. That you could think about, SMC, etc. That is obviously also running there. You can choose that. It's just the neat thing about Excel is in many cases it's not necessarily the biggest, massive, millions of lines of code simulators.
No, yeah, exactly.
So the real work so far has actually been to just make sure that it actually integrates properly. It's very much in the future set of decisions to and on our roadmap to add more inference algorithms, but also we want to make it so that you can plug in different even languages and make a universal set of, let's say, cross-compiled sort of languages, maybe where you can add your favorite of the language, maybe, as well as having like an intermediate layer, so you can plug in and have some open source capabilities, which we don't have that yet. Right now, it's just about let's make sure that it actually works properly, and that we can support the sort of the proprietary bits first, and then we can expand from there. But that's the goal. I mean, we want to make it so this is much more of a platform-like system. that you can also plug things into and, add your own inference algorithms if you want.
Yeah,
Obviously.
yeah, exactly. So for sure, you're gonna handle mostly, let's say, beginner level models here, and probably like conjugate priors models. This is a perfect use case. And
There's
yeah, if you're
all
starting
sorts
to
of
have,
cool things you can do. I'm quite
yeah,
excited about the things you can do.
yeah,
Exactly. There's a lot of really, really
yeah,
cool, both science, but also just the technical stuff as well. It's actually a
hmm
lot of fun.
yeah,
And
yeah,
it's a
yeah,
weird thing. It's like Excel is fun again in some weird way. Like I actually enjoy writing these
yeah,
models because it's quite fun
yeah,
actually.
yeah. Yeah, I mean, even for the hard models, like, I can definitely imagine that being offloaded to Evara, basically, and Evara being able to basically parse a prompt from the user directly in Excel, and then basically sampling, like defining and sampling, let's say, a structural time series model, sampling that with PyMC under the hood, and then in a few minutes giving the user back plots and analyses if everything went well. And then, yeah, basically the user not needing at all to know what went on.
And that's what we're doing here also, right? It's exactly that.
Yeah.
We want to make it. What we're trying to do with this is just deliver on that promise that it's supposed to be something that you can have in your everyday tools where you don't need to be a statistician, that don't even know what probabilistic programming is.
Yeah.
Like the idea is to make this look like a set of macros that sort of fits nicely into Excel, but take away even the complexities of the tool itself and what it does, which sometimes can actually be sort of both a benefit and not, because it can also look too pedantic a little bit. It's like, is this just like a simple like add-in that does whatever? And it's like, no, there's a lot actually also going on. But we want to hide that. But it can also be like, well, is there anything interesting really going on then, other than just something like that? So, which is a funny place to be. It's like, and like I said, the barrier of adoption is the biggest problem that I am trying to figure out. If anyone has great ideas of your listeners, yourself, Alex, this is the thing I want to figure out, is to get people to use these sets of tools. And it's whether it's what we're doing or something else is actually, that doesn't matter. I'm in this because of the years. Like I think most of both yourself and your listeners, it's about Bayesian inference.
No, exactly. Well, I mean, so how people listening to us right now, if they're interested in trying that out, how can they do that?
You just
how
send us
can
an
people
email.
start using
More than
Evara?
welcome to.
And
We've got a website, but send us an email and we'll figure something out.
awesome. What's the email?
It is either contact@evara.ai.
Perfect. Yeah. So
I'll give you the context also for the notes as well.
Yeah, the website and the LinkedIn of Evara are in the show notes for this episode, folks. So feel free to focus on that. And actually, to start playing us out here, Andreas, because you've already been very generous with your time, but I'm curious about, I've been part of the team who's created and founded a company. So I'm always the entrepreneur in me is always interested in this. Like, where are you in the company's life cycle right now? What are your priorities for the next month? And yeah, what are you focusing on right now and your next step?
Oh, there's been some just restructuring that we've had to do, and it's like I said, the struggle is to figuring out how to convey the ideas of what we're sort of offering, which has been difficult. So we've been focusing a lot before on big enterprises, which has proved both difficult because it turns out enterprise sales are very hard. It's what you realize. They're very difficult. There's a lot of sales cycles and everything. So we've now got some sales help involved as well. But we might want to try to scale things around and sort of target maybe more medium to small businesses. But otherwise, analysts, just get people to use it. I think that might also be one of the important factors to sort of get back to maybe it also has to be an internal, not pressure is not the right word, but if analysts can use it, we can maybe better and more easily convey it because it can sort of generate value and interest from sort of an internal aspect rather than trying to to sell directly to very busy executives, right? Because they certainly don't have the bandwidth, which is, why would they? It's like, we all know when we're busy. It's not like I'm going to drop everything. Like, imagine I'm sitting here on like the analogy might be a Windows machine, and now someone convinced me that Linux is better, but it's like, yeah, but I don't have the time to figure out Linux. It doesn't matter how good it is, right? It's I don't have the bandwidth necessarily to make that decision at the point in time. So yeah, it's figuring out how to sort of really get into the market with something like this. That's everything that I'm really to figure out these days.
Yeah,
We've actually just today finished a new update, which is wonderful before we got on the call. So that's
awesome.
Yeah.
Wow. Yeah, congrats. Well done. I know it's hard, and I know it's a lot of stress and work to do that. Especially the sales funnel is always obviously something that you need to pay a lot of attention to. So,
and I'm
I think you guys are doing
it's,
yeah, exactly. Yeah. But I think you guys are doing a very good job on that, and I think it's a great initiative. I know from the show that a lot of people have been asking for this kind of product. Well, now it's here, folks. So if you wanna try it out, go to the Evara website. And actually, just before asking you the last question, Andreas, you are someone who is curious and always learning. So, yeah, is there anything you personally are focused on for the coming month? Things you want to learn, things you are curious about, or you want to see in particular?
I'm getting more and more interested in not to open another can of worms, because, I'm going to say LLMs, which is, you can't not say that, I feel like. Even though I will say I've been trying really hard not to. Like, I have always
good. That's good, because that way the show goes up and more people listen to it.
Brilliant. That's right. That's fine. I've always been a bit of an anti sort of hype person, just sort of generally. I like to be somewhat skeptical, I guess, for better or worse. It's one of those things. But I like to believe that I approach these things somewhat conservatively, and yet still with an open mindset. And I've been more and more intrigued with, I think, ways that we might be able to leverage the language models to sort of really succeed in our mission, as well as sort of like a part of a way to communicate maybe the kind of inference stuff that you might be doing. I think there is some potential there, and we've done a lot of exploration. That's the next thing also we're going to be working on, is to figure out a way to do that. But what I want to make clear, it's like one of those things where right now we don't have any LLMs, right? I mean, and it's not like that. It's programming, and we're not going to have LLMs replace that ever. But I think there are opportunities where you can have, again, it goes back to that interface aspect, where I think there's some interesting things there that we're exploring, if we can make sense of this in a way that is actually useful. But we always try to do, and what I'm always wary of is where are the shortcomings with these systems? And are you going to run up against a wall where it's going to introduce errors and bugs into your, like, the way you think about your problems, etc. So I think it's one of those things that we need to be very careful of in how you integrate these systems in a way that it makes sense. But that's one of the things I'm really excited about. Actually, I think that will be it's a lot of fun to look at.
Yeah, definitely sounds like it. Awesome. Well, Andreas, I'm gonna call it a show, because you've been, again, super generous with your time. Thank you so much for these. Of course, as usual, before letting you go, I'm going to ask you the last two questions I ask every guest at the end of the show. First one, if you had unlimited time and resources, which problem would you try to solve?
Well, I think this is one of those that I think they've already been said before. I'll just do better inference.
Oh, no, I don't think so. No. Yeah.
I think Daniel said something, maybe not exactly the same, but I will agree. I'm envious of those people working on good inference algorithms. I think it's the feeling of generating new methods or algorithms and seeing it working is, there's nothing quite like it. I guess why we do also science partly is you end up like it's just so enjoyable. I mean, the surrogate model is that example also is like what do you use it for? That one was also just because it was super neat as a science, but there is a problem to be solved with inference and better inference and faster inference, which is one of those things that I think we should really, I would love to try and solve that. And obviously figuring out how to maybe do mass scale, I don't know, research and questionnaires and figure out why inference and Bayesian inference and statistics is so difficult to conceptualize for people. I think that's another one you gotta figure out.
Yeah.
But I think I would say, just so you know, Alex, I think what you're doing here is amazing. I think this is indeed one of the ways to do it. And I think I wish more people they should start listening to your podcast. This is brilliant.
Thanks, Andreas. Definitely appreciate that. And feel free to spread the love. That's how the show that's how the show gets going. I actually don't do any paid marketing at all. It's just like only organic growth, So this is a purely organic product. Could be sold at the Whole Foods if I understood correctly. So that's perfect.
Brilliant. Yeah, you're doing some really good work. I think this is brilliant. I really love this. I think it's great.
Great. Thank you, Andreas. Definitely appreciate it. And well, second question, we can't, I'm French, so I have to talk about food all the time. So if you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be?
All right. I thought you just dinner generally. I was like, I would love dinner. It's just, it's a struggle. But no,
that's better.
I think, I think that's like, it's between two different people. One is Newton. I mean, that is just what he managed to accomplish is just ridiculous. It's I gotta figure out how that meant. Like, you just don't invent calculus because you want to try to solve all the problems. Like, who does that? That's just insane. Was even before 30 or whatever? It's like, wow, talk about feeling like you got to work harder. I think he just showed up everyone. So I think that would be pretty interesting conversation. That was how to like figure out how that man thought. That's quite something. But the other one would be, I think, Niels Bohr. Well, he's Dane, so I can't help it. And in fact, I was his grandchildren were teaching at my the university. So he taught his Thomas Bohr was taught me electromagnetism. Very difficult subject, but fascinating. I mean, to figure out how you think about quantum mechanics, talk about uncertainties. It's like here we have nature's own uncertainty in quantum mechanics. I want to talk to that man. I'll figure out how do you, what's going on there? Like how do you start to reconcile the world with being quantum fluctuations and random? I think in physics, quantum mechanics was one of the most enjoyable subjects that I worked on. I really like that. Maybe that's why I ended up in Bayesian inference, I suppose.
Yeah, that's that makes sense for sure. That'd be a fun dinner. Yeah.
I need to ask you then, Alex. Maybe you've already answered. What about you?
Oh yeah, I've already answered that. I think twice at least.
Really?
So that would have been episode 0. But that's great. That means I can answer multiple times. I think episode 0 I answered, and then episode 57 I was actually interviewed by Remy Louf, who was on the show.
Your is impeccable. Well, you just know the exact numbers. That's pretty wild.
Yeah, I know. I mean, each episode is a substantial amount of work. So at some point, like each episode you ship is a bit like its own product. So it stays with you. So I often remember the numbers of the episodes. Yeah. That's a weird way my brain works. So that's for sure. But yeah, I mean, so that's what I answered. I don't even remember what I answered in episode 57. I'm pretty sure I answered Condorcet for episode 0. So because French mathematician, also part of the Enlightenment, extremely brilliant person. From aristocracy, but who actually also was an extremely adept thinker of democracy and republic, and his ideas for the time were extremely advanced, especially from someone coming from aristocracy. So I was definitely someone who knew how to think outside the box, because that is definitely, his idea were definitely not how he was raised. But at the same time, he also proved mathematically the problem of majority voting when you vote the way we do. And so, yeah, basically, he was already advocating at the very, very beginning of democracy that we shouldn't have simple majority votes like that, because this is not the actual way of actually getting to the majority vote. And so we should have much more ranked voting. So this is one way. The one he was mathematically proving would be the optimal one would be basically to select your preferred candidates in some duels. So, and so just 2 by 2, but each candidate would be in duels, and then the candidates who wins the most duels is the candidate that is actually chosen by the majority. And
what time period was in? What are the nature of these duels?
yeah, exactly. I mean, they still had actual duels, so I'm pretty sure it influenced his thinking. But yeah, mathematically, he basically shows that it's the optimal way of actually getting to the majority vote, because otherwise there is dilution of votes and there is strategic voting. You can see that in France, for instance. I mean, even in the US, but the Electoral College adds a layer of complexity. But in France and in most of Europe, there is strategic voting, because basically if there is more parties from, let's say, the number of right parties stay the same, but you have more propositions on the left. So if you have more leftist parties, then actually it's going to dilute the vote for the left, even though actually the fact that there is more propositions from the left probably is because people are most interested in the left's propositions. But the fact that you have more parties means that the left actually has less chance of getting to power, even though it may represent more than 50% of the population. And so that's a big problem. And here I'm saying left, but it could be right. It's like math is blind.
I understand.
Yeah.
It very well illustrates the example.
And that's
fascinating.
Also and that's also why, like in the US, you cannot really have more than 2 parties, because then it's diluting your votes and so on. And Condorcet's whole point is that, well, it shouldn't be the case. Like we don't know if the majority vote is the best one, but if you actually want the majority vote, then do it properly. And the proper way to do that is Condorcet voting, so it's just like preferred for each duel, and then the winner of the duels wins the election. There is one paradox, though, of these, is that, for instance, if you have 3 candidates and A is preferred to B, who is preferred to C, who is preferred to A, then you have a Condorcet paradox, and then there is no winner. And the way this is solved is a random solution. So just draw randomly the winner. And this is a fun way to do that. So I think that's why it will never be implemented, because we hate randomness, and it would be like, no way the president is chosen randomly. But it's actually the fairest way to do it when there is the Condorcet paradox. It's just between the ones who've got the most duels, you just draw randomly between them, which as a Bayesian I could only appreciate. Yeah,
fascinating. I think I would say, Alex, there in the end, I think it's a marketing problem. You just have to call it gambling. I think people like some sort of randomness. I'm pretty sure.
Yeah.
It depends on how you frame it.
Yeah, exactly. Well, this is another can of worms.
It's a total can of worms, but for sure. I don't want to go down there.
So, I mean, and so since you asked me, I don't remember who I said for episode 57. So, maybe I said it already, but of course, I would really like to have dinner with Pierre-Simon Laplace, who is actually the one who developed Bayesian statistics and understood the potential, and who is actually someone very interesting, like from very like a very small family from the west of France. So he didn't have a lot of money coming. I think they were peasants. So you can imagine at that time the living conditions. And he just managed to go to Paris because he was a brilliant mathematician. And it's just his math teacher who, like spotted him and was like, dude, you could apply for, I'm sure they were saying dude already at the time. So he was like, dude, you got to go to Paris, take the train,
especially
even
in
though it
France,
doesn't
like you
exist
say
yet.
dude, for sure.
Yeah. It'd be like frère.
Yes.
Frère, you need to go to Paris and study math at university. And then he studied math with D'Alembert, who was one of the brilliant minds of the time. Actually found out about base roll, but like he didn't read about it. He just discovered it again, and was super happy and thought he would make his doctorate thesis about that. And then D'Alembert was like, "Oh yeah, well done." But it actually already exists. So
but
yeah,
you're a little late.
you cannot write your PhD thesis about that. And so actually Laplace was a bit depressed about that, if I remember correctly. He was quite down and was like, damn, I don't know what I'm going to do with that PhD. And then that's when, the obstacle is the way. So that's when he understood the whole framework about that and developed all of that. So I think that'd be a great dinner because extremely brilliant person from modest roots. So I would be actually super interested in, how you lived at that time in these conditions, and who was also able to raise himself up just because he was extremely brilliant intellectually. And like, then the dinner would be in French, so I'm sure I would understand him, even though sometimes, he would use weird words in French that I think
like dude and
stuff.
stuff.
But yeah.
No,
So
that's
yeah, Laplace would be
very
my
good.
choice.
That sounds amazing. I'll just get, if you have room for another, I wouldn't
Sure.
mind joining in on that. I mean, I don't understand French. I'll just sit there, I guess. But
Yeah, well, happy to. I'll translate. That'd be great.
wonderful. That would be fascinating. That was a good choice. Yeah. It's,
Yeah. I mean,
brilliant.
bring Newton. I'm pretty sure he'll be happy to meet Laplace and conversely. So
Yeah,
let's
it
do
would
that.
be. It would be. We'll have a ball. We'll just. Yeah, I love it. I think it's great.
Awesome. Well, Andreas, this is definitely running long, and I need to let you go. So thank you so much again for taking the time. Good luck on Evara. Thanks for doing that. I think it's a great service to the community, and I hope you guys will be successful. I definitely wish you the best. All the links are in the show notes, folks, for those of you who want to dig deeper. And Andreas, thanks again for taking the time and being on this show.
Thank you so much, Alex. It's been an absolute pleasure. And I think what you're doing is it's brilliant for the community and everything that we're all trying to do. So keep this up. This is great. Thank you.
Thank you. I'll stop the episode on that for people who just watch the end. That makes me look very good. So awesome. Thank you, Andreas, for doing exactly what I asked you before the show.
Yes. It was lots of emails and lots of documents that instructed very carefully.
Don't spill the secrets. See you soon, folks. This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and follow the show on your favorite podcatcher, and visit learnbaystats.com for more resources about today's topics, as well as access to more episodes to help you reach true Bayesian state of mind. That's learnbaystats.com. Our theme music is Good Bayesian by Baba Brinkman, feat MC Lars and Megaran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. You can support the show and unlock exclusive benefits by visiting patreon.com/learnbaystats. Thank you so much for listening and for your support. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.